today's lecture, our main aim is to discuss how to introduce a suitable topology on x1 cross x2, where x1 we have a topology tau 1 on x1, x2 we have a topology say tau 2, and in a natural way we call it the function P1 from the Cartesian product x1 cross x2 to x1. Aim to introduce a topology say tau on the Cartesian product x1 cross x2, which makes P1 from x1 cross x2 with respect to that proposed topology tau to x1 tau 1 defined as P1 of order pair an element in x1 cross x2, P1 of order pair x1 x2 equal to x1, which makes this function continuous. Similarly, which makes we call it Pi from x1 cross x2 tau to xi tau I, that case defined as Pi of order pair x1 x2 equal to xi I 1 or 2, and we just do not want to define just any arbitrary topology tau on this Cartesian product. That case the easiest thing is one can define the largest topology, namely the discrete topology. So then whatever may be the open set here, the inverse image with respect to this function will be some subset of x1 cross x2. The topology is the discrete topology, then every set is open, then that case such a with respect to such a topology each Pi will be continuous, but we do not want such a larger collection, the tau should not contain such a larger collection of open sets. This should be the smallest such topology, which makes each Pi is continuous. So meaning is, what is the meaning? First condition is each we want to define a topology on x1 cross x2 having the property that each Pi, these are all called projection function in a natural way. If you are in R2, we take a order pair x1 x2, project this is our x1. So and suppose tau prime is a topology on the Cartesian product x2 having the same property, that is satisfying the following properties, namely each pi from x1 cross x2 with respect to this topology tau prime to xi tau I is continuous for all I 1, 2. So, then we want that our topology is the smallest such topology, then this tau should be weaker than mean tau subcollection of tau prime. Such a topology tau we will call the product topology. So, this is our requirement. So, in fact it is not only for two topologies or any, first we will see for a finite collection whenever x1 cross xn. So, we have a collection of topological spaces xi tau I. Let us assume that I finite, the collection is finite, I varies from 1 to n. So, and exactly then same way, only here pi, that case we use the notation pi is a function from say pi xj, j varies from 1 to n from 2 that ith coordinate space with the topology tau I. This is defined as pi, an element here is of the type p suffix I x1 x2 xn, then image of that is that ith coordinate xi, that belongs to capital Xi. Then we want that such a pi is continuous with respect to the topology tau, and whenever tau prime is a topology on this Cartesian product pi xi I 1 to n satisfying the condition that pi xj j 1 to n, this is same as x1 cross x2 cross etc. cross xn to xi should be continuous, and in that case this is continuous, then this implies tau should be tau prime. Yeah, then such a topology we will call it product topology. So, how to define such a topology is quite natural. So, we have, that is definition. First let us see for 2. So, given x1 tau 1 x2 tau 2 topological spaces we call it capital X is x1 cross x2. Our aim is to make each such pi continuous, or more generally we can take given xn tau n topological spaces, then capital Xn. So, what will happen if p suffix xi from x1 cross x2 cross xn to xi should be continuous. That means this is continuous mean inverse image of open set, that is if you take ui open set here, that means ui belongs to tau I, then that should imply the inverse image p I inverse ui should be open in pi, sorry, should be open in our proposed topology tau, that means this should belongs to tau. So, we will collect all such pi inverse of ui. So, keeping this in mind, we define what is the collection first. What do you mean by pi inverse of ui equal to, by definition, set of all say x is in our Cartesian product x1 x2 xn belongs to capital X such that pi of x should belongs to ui, pi of x belongs to ui, but by definition pi of x is ith projection, so that is xi. So, here we have the collection of element order n tables x1 comma x2 xn, the only restriction is xi should belongs to ui, there is no restriction on other elements. So, other elements can be any arbitrary elements from the corresponding capital Xi. So, this is EC2, that is, see that this is same as capital X1 cross xi minus 1, ith place should belongs to ui, this is same as this cross xi plus 1 cross xn. So, this pi of ui equal to this set and our I varies from 1 to n. So, in fact we collect, we call it say script suffix si. This collection is set of all pi inverse of ui such that ui belongs to tau I, and call it script s, use union of such si, in this case I varies from 1 to n. So, now this, if we take the union of such, see in particular in fact union of a belongs to script s equal to the whole space x. In fact what will happen, take any I or in particular take P1 inverse of P1 is a function from this Cartesian product x1 cross x2 to xn to x1, I is 1, then take an open set ui belongs to tau I, in particular the whole space xi. So that is P1 inverse of x1, this is same as now ui equal to xi, here I equal to 1, then this will become x1 cross x2 cross xn. That means this the whole space is in fact belongs to, in this case S1, and the same thing for true for any I. So in fact we will see that we will define, you are given a topological space x tau, then from a subcollection, that is what we know, we have seen that how to generate a topology from a subcollection. From that we will generate a topology, for that topology script beta will become a subcollection. In fact we can go for still smaller collection, just X is any set script S a subcollection of power set of X. Suppose we assume that this union of such a from script S equal to the whole space, then we say that such a collection script S is a subbasis, that is if union A from script S equal to the whole space, then we say that script S is a subbasis for a topology, this I am writing for a topology on X. That means from this subcollection will generate the a unique topology. For that, in fact if you see the definition, this is the first condition of our basis, when a subcollection will form a basis for a topology. So if we take script beta is the collection of all possible finite intersections of members of script S. Beta is the collection of all possible finite intersection of members of script S, then such a collection script beta, then this is exercise, then script beta is a basis for a topology on our Cartesian product, on more generally here just on any set X on X. So this will hence generate a script beta will generate a topology on capital X, and this topology is called the topology generated by the script S, and that script S is called a subbasis. That is why from a subcollection, if it satisfies only this condition, each union of members of script S equal to the whole space capital X, then that will generate a topology. So, keeping that in mind, so now we will erase this. So, we have a collection script S. Now, this collection script S will form a subbasis for a topology on phi xi I1 to n, and this topology is called the topology tau on this Cartesian product X generated by script S is called the product topology, on X. So, we have defined a topology in a natural way. Now, with respect to this topology, that is why we wrote in the beginning, we want to define not just a topology, we have defined this unique topology which has these properties. So, now we have see each P I. So, for example, when n equal to 2, P1 is a function from x1 cross x2, x1 x2 topological spaces to x1. Is P1 continuous? Yes. Keeping that in mind, we have defined the topology which we have called the product topology. See what is here? Take any open set U1, so belongs to tau 1. Then the inverse image, then P1 inverse of U1, we have seen that is nothing but U1 cross x1. By definition, I mean we have collected all those subsets in script S. So, in fact this is such a set is called subbasic open set. So, they are all, in particular we have script S will be a subcollection of script beta. So, in particular you take any member A belongs to script S. Once it is a subbasis, our index set is 1, I equal to, take I equal to singleton 1 and A1 equal to only A. So, only intersection of AI, I equal to singleton, I belongs to singleton 1 means that is A1. So, the by definition script S will be a subcollection of script beta, and we know that will subcollection of tau beta. This is our product topology. So, we have taken care that with respect to that topology this is continuous. So, now we wanted that it is not just makes each pi is continuous, it is smallest such topology having this property. So, that is now take any topology, suppose say tau prime is a topology on phi xi, I varies from 1 to n, we will just call it capital X, satisfying the property, namely for each I Pi function is same, the projection function from capital X to that ith coordinate. Now continuous with respect to this topology. So, we will write x tau prime to xi tau I. So, satisfying this condition, namely for each I this Pi is continuous, this is given. Then to prove is the product topology tau should be weaker, is weaker than all such topology having this property. So, we have to prove that if u belongs to tau, then u belongs to tau prime. So, take u belongs to tau is any open set. First, in fact, what is enough to, if you want to prove some topological space is subcollection of tau prime, in fact, enough to prove that the corresponding basis scrid beta is a subcollection of tau prime. So, we have generated tau from scrid beta, and in fact, we have still smaller subcollection, that is subbasis script S. First, let us prove that the subbasis, this particular subbasis script S is contained in tau prime. So, take, so what is script S? Script S equal to union of script Si, I varies from 1 to n. So, take u belongs to script S, then u belongs to at least one Si, script S suffix Si. But what is this? This will imply u will be equal to p suffix I inverse of ui for some ui belongs to ui belongs to tau I. But what is given for us? This Pi from x tau prime to xi tau I is continuous. So, we have now ui belongs to tau I and Pi is continuous, hence the inverse image is open set. Now, this p suffix I from x tau prime to xi tau I, still I will write in short, continuous, ui open in xi tau I implies Pi inverse of ui is open in the domain, there the topology is tau prime. So, that is what we wanted to prove. If we take a u belongs to S, then u belongs to tau prime. That is, we have proved that the script S, the subbasis script S is a subcollection of tau prime. Now, what is our, from the collection script S we got scrid beta. Now, using this let us prove that scrid beta, next step 2 let us call. Step 1 is we have proved that script S is subcollection of tau prime. Now, take we aim to prove discrete beta subcollection of tau prime. See, that is quite obvious because A belongs to discrete beta implies what is by definition discrete beta contains the finite intersections of members of discrete beta. So, A belongs to discrete beta imply there exists a finite is important, there is a finite index set, okay, we call it index set, that may be even empty, finite index set J such that A can be written as finite intersection. So, we call it A equal to intersection of such U belongs to or we call it U alpha belongs to the index set J, where each U alpha belongs to script S. That is, we are able to write A as a finite intersection, here our index set is finite, of members of script S. But already we have proved that that is our step 1, we have proved that script S is a subcollection of tau prime, hence this implies each U alpha belongs to tau prime, that will imply the intersection, a finite intersection of open set is open. So, that implies this A intersection U alpha belongs to J, that is what our A belongs to in tau prime. So, there we are using the fact that tau prime is a topology, each U alpha is in tau prime imply the finite intersection of members of tau prime is again in tau prime. So, this imply A is in discrete beta implies A is in tau prime, that is, we have proved that the discrete beta is subcollection of tau prime. Now, in fact, using this it is immediate that the topology generated by discrete beta is again a subcollection of tau prime. This is what our product topology, here we have just to say tau, we are denoting that by tau. So, take any, see how to prove, take A belongs to tau. So, if A is empty set is in tau prime, so assume that A is non-empty. So, A is non-empty means you have to prove that it is in tau prime, it is open in X tau prime. So, we will prove that each point of A is an interior point with respect to this topological space. Now, take X belongs to A, but what is our condition? A X belongs to A imply X will belongs to, see this X, A belongs to tau, X belongs to A, this implies there exists a basic open set. So, that is here there exists B from discrete beta such that X belongs to B contained in A. But that is how, yeah, we have defined the, because it is a basis, some x is A is open mean for each x in A there exists a basic open set discrete beta such that x is in B contained in A. A belongs to tau mean for each x we will get a basic open set containing x contained in A, but we already have discrete beta is contained in tau. Hence, B belongs to tau prime because it is in tau mean we have proved that it is in tau prime. So, hence B belongs to tau prime is such that x belongs to B which is contained in A. So, the only difference now is for a given x in A there exists B from tau prime containing x and contained in A, that means that x is an interior point. So, and A is on for any x in A, x is an interior point of A with respect to tau prime. That will imply this gives us, this proves that A is open with respect to tau prime. So, that is what we wanted to prove, that is A is in tau imply A belongs to tau prime. That is we have proved that the topology we have defined on the Cartesian product x1 cross x2 cross xn is such that it makes each projection function pi from the pi xj to xi continuous, and it is the smallest with respect to that product topology tau. Each pi is continuous here tau I, and it is the smallest such topology. This has many, this gives now a way of constructing new topological spaces. So, once you are given x1, x2, xn, then this will give a new topology, that is what like we have R, the usual topology, R with usual topology, then R cross R, then here we can now define the product topology. In fact, see we can see directly what is discrete beta is. If it is finite intersections of members of that collection Si, but what are the members of here is of the type some u, if it is ith place we have seen that x1 cross x2 only the ith place ui, all other place the whole space. See for example take n is 2, so the one sub basic open set is of the type u1 cross x1, another sub basic open set will be of the type x1 cross u2. Here if we take the intersection, so this we can prove that this is same as u1 intersection x1 cross u2, here the u1 intersection x1, here it is x1 here the note, yeah. So, u1 cross x1, here x1 cross u2. So, here we will write the notation, here it is u1 cross x2 as a basic open set, here x1 cross u2. So, u1 intersection x1 cross x2 intersection u2, but u1 subset of x1, So, this is U1, U2 subset of X2, this is U2. That is, in fact, we can prove that exactly this is true for any finite intersections of members of script S. The script beta will be of the type set of all U1 cross U2 cross UN such that Ui belongs to tau I varies from 1 to n. In fact, so even we can directly start with this collection, say script beta, then this collection is a basis for a topology on x1 cross x2 cross xn, and that topology generated by script beta is what our product topology. That is other way of defining, but for us the main motivation is we want that our product topology is such that it makes each pi is continuous and it is the smallest such topology. So, now from that we get that the script beta will be of this type. So, it is enough to know what are the basic open sets. In fact, in all this course throughout, see, we introduce the concept. I will quickly now recall. So, when we started with after defining the topology, our aim was to define a subcollection of power set of X, then it has two properties. You give any X in the whole space, X will be in some B. Then we have seen that if B1, B2 are in script beta and X is in the intersection, then there X is B3 which is contained in B1 intersection B2. Then we proved that that collection will generate a topology. In fact, this is called the topology generated by script beta. So, also now it is, I will leave it as an exercise. Now, suppose given is X tau topological space, this is given. Now, script beta a subcollection of tau, and this collection is such that this collection beta already it is a subcollection of tau, further is such that A belongs to tau if and only if for X in A, for X belongs to A, that means when A is non-empty and X belongs to A, for X in A there should exist a member from script beta such that X belongs to B which is contained in A. If this condition is satisfied, then script beta is a, then so I leave it as an exercise, script beta is a basis node for a topology on X, for a topology, say that topology we call it tau suffix p, and further the topology generated by this collection is same as the starter topology. So, already we know that script beta is subcollection of tau. So, this how we define from if script beta is a basis for some topology, then this how we define an open set, set of all A subset of X such that X in A imply there X is B such that X in B contained in A. So, this will coincide. So, and then we define what is called take a subset interior point. What is an interior point? First it is in A, X belongs to A interior if and only if there exists a basic open set. So, let us say that means now we know that X tau topological space and script beta basis for X tau. Now we can say either from script beta we got it tau, or we know tau and we have a sub collection satisfying these properties. In either case, that we call it that sub collection as a basis for X tau. Then these are all exercise, that is from the basis we can, that is that much if you know what are the basic open set, from that we can define what is an interior point. X is an interior point if and only if there exists a basic open set such that basic open set containing X contained in A. Similarly, if you say that X is a limit point, in short, for X in X, X is a limit point of some subset, A subset of X, if and only if it satisfies the following properties, namely for each basic open set. What we want to stress is need not be for every open set, for each basic open set U, okay, for each basic open set U containing X, U intersection A difference X. It is enough to prove for the smaller collection script beta this. Similarly, all these properties, then even if it is continuous, F from X tau to some Y tau prime continuous, and we know that script beta a basis for tau prime. Then F is continuous if and only if F inverse of V is open in the codomain, that means it belongs to tau for all V belongs to the basic open set. Need not be, I mean once using this we can prove it is true for all open sets in Y. In fact, here what is still important is, even if we know a script S is a subcollection of power set of X such that union of A in script S is the whole space, then we say that then we call script S then is a sub basis for a topology on X. Then we have seen how to generate such a topology. From script S go to all possible finite intersections of members of script S, then from there go to topology. Now it is easy to prove that this F from X tau to Y tau prime continuous here, where script S base a sub basis for tau prime. That means from script S we have generated the topology tau prime, then F is continuous if and only if inverse image of sub basic open set is open, for all this is enough. So using that we can prove that inverse image of every open set is open. So, that we will leave it as an exercise. So, what is interesting here is many times we will be more familiar with only either a subbasic open set or basic open sets. From there we can derive all the properties, and remaining part we will see in the next lecture. Thank you.